This video is Module 5, Number Systems, for the Cisco Netacad Intro to Networking course. In this module, we're going to look at two objectives, the binary numbering system and the hexadecimal numbering system. First, we have the binary number system. The binary numbering system consists of ones and zeros called bits, and the decimal numbering system consists of digits 0 through 9. Host, servers, and network equipment using binary addressing to identify each other, or they use that. Each address is made up of a string of 32 bits divided into 4 sections called octets. It's pronounced octets. Each octet contains 8 bits or 1 byte separated by a dot, or it's also called dotted decimal. For ease of use, the dotted notation is converted to dotted decimal. So you'll have something called 192.168.10.10, but then that gets converted over here to ones and zeros. Positional notation means that a digit represents different values depending upon the position the digit occupies in the sequence of numbers. The decimal positional notation system operates as shown in the tables below. So if we have 3, 2, 1, calculate 10 to the third power, 10 to the second power, and then we would have thousands, 100, 10, and 1. The positional value is 1,000, 100, 10, and 1. The decimal numbers, we can calculate that, we can add them up, and then we get the result of 1,234. The binary positional notation system operates as shown in the tables below. So the position in the number is 765432110. You'll notice that we work from the right to the left. We can calculate 2 to the 0th place, 2 to the 2nd place, 2 to the 4th place, and so on. The position value is 1, 2, 4, 8, 16, 32, 64, 128. You'll notice that it doubles each time as it goes in the position. And when we look down at the chart here, the binary number of 11000000, we would put that in, and so we would count 128 because that position is turned on. We would count 64 because that position is turned on. So we would have 128. We'd have 164. We wouldn't have anything over here, so we would get 128 plus 64, which would give us 192. We can convert binary to decimal. The way I do it is I write a chart out and I start from the right and go to the left. 1, 2, 4, 8, 16, 1, 2, 4, 8, 16, 32, 64, 128. When I go in for an exam or I need to do binary to decimal without a calculator, I write this down on paper. And then when I need to convert my binary number, I can just write my numbers in, fill in my zeros, and then I can say that's 128 plus 64 gives me 192. And then I can go to the next one and say that's 128 plus 32 plus 8, that's 168. And here I'm going to say 00001011 is 8 plus 2 plus 1, which gives me 11. And then down here, 1010 is 8 plus 2 gives me 10. The binary positional value table is useful in converting a dotted decimal IPv4 address to binary. We start in the 128 position, and that's the most significant bit, is the decimal number of the octet. Is it equal or greater to 128? If it's greater, then it will not fit in this value. So we add a 0. If it's no, if it's yes, then we add a 1. So if it's 192, we add a 1 there. So we record 0 and 128, the positional value, and we move to 64, and we say, is the number that we have left over greater than 164? Is it? If it is, we then mark a 1, subtract 64, and then with the remainder left over, we keep moving down until we get to 0. And here it is. So is 168 greater than 128? Yes. So we put a 1 in there. And then that leaves 168 minus 128 leaves us with 40. So is 40 greater than 64? No. So we put a 0 in there. Is 40 greater than 32? Yes. So we write a 1 in there. And we say 1 in the 32 position, we subtract 32 from 40. So 40 minus 32 gives us an 8 remainder. And so we say, is 8 greater than 16? No. Is 8 greater than 8? No, but it's the same number. So we write a 1 in there and we subtract 8 from 8, which leaves us with 0, and the remainder of our places are 0. Routers and computers only understand binary numbers. Humans work in decimal a lot easier, so that's why we use dotted decimal, but the computer converts it to binary on its side. Next, we're going to take a look at the hexadecimal numbering system. With hexadecimal, to understand IPv6 addresses, you need to understand hexadecimal. So we need to be able to convert hexadecimal to decimal and back and forth. So hexadecimal is a base 16, decimal is base 10, binary is base 2. And so hexadecimal being a 16 numbering system, we use the letters or numbers 0 through 9 and letters A through F. So it's easier to express a value as a single hexadecimal digit than as a 4 binary bit because it makes it smaller and easier for us to read. So hexadecimal is used to represent IPv6 addresses and MAC addresses. So when we convert that, hexadecimal 0 is 0 all the way across, but F in binary would be 1111, and in decimal it would be 15. IPv6 addresses are 128 bits in length, and 4 bits is represented by a single hexadecimal digit. That makes the v6 address a total of 32 hexadecimal values. And the figure showed here, the figure shows the preferred method of writing out IPv6 addresses with each X. Each 4 hexadecimal character group is referred to as a hextet. So if we follow the steps listed to convert decimal numbers to the hexadecimal value, we convert the decimal number to 8-bit binary strings. We divide the binary strings into groups of 4, starting from the rightmost position, and then we convert each 4 binary numbers into their equivalent hexadecimal digit. For example, 168 converted into hex uses a 3-step process. 168 in binary is 10101000. One in that same number, and 2 groups of 4 binary digits is 1010 and 1000, and 1010 is a hex of A, and 1000 is a hex of 8, so 168 is A8 in hexadecimal. If we follow these steps to convert the hexadecimal numbers to decimal values, we convert the hexadecimal number to a 4-bit binary string. We create an 8-bit binary group starting from the rightmost position, and then we convert each 8-bit binary grouping into their equivalent decimal digit. So for example, D2 is converted into a decimal using the 3-step process. D2 in a 4-bit binary strings is 1101 and 0010, and that number and 0010 is put together as 110 10010 in an 8-bit grouping. And so that binary number is equivalent to 210 in decimal. So D2 is equal to 210 in decimal. So what did we learn in this module? And you're going to do a lot more in the class, by the way. This is just the presentation and overview for those students that need a refresher or were not able to make it to the seminar or to the actual class time. So what did we learn in this video is that binary is a base 2 numbering system. Base 2. It consists of the numbers 0 and 1 called bits. Decimal is base 10 from 0 to 9. Binary is what host servers and networking equipment use to identify each other. Hexadecimal is a base 16 numbering system from 0 to 9 and then A through F. Hexadecimal is used to represent v6 addresses. v6 addresses are 128 bits long, and every 4 bits is represented by a hexadecimal digit for a total of 32 hexadecimal digits. And then to convert hexadecimal to decimal, we must first convert to a hexadecimal to binary, and then we convert binary to decimal. And then the other way, we convert decimal to hexadecimal, and then we convert the decimal to binary, and then the binary to hexadecimal. These were the new terms that we learned in this module, and I'm going to leave this screen up for a few seconds so you can pause it. And thank you for watching my videos, and I hope you have a great day.